So recently I've been learning assembly, specifically x86-64 using GAS, the GNU assembler. I guess it's kind of like my little way of rebelling against AI. The higher level they try to take me and the further they want to push me away from the code, I go in the opposite direction and I dive deeper and deeper down the stack. So as I've been exploring some of these lower level concepts, something that has piqued my interest over the last few days is this thing known as the red zone. So the red zone is basically like a 128-byte safe area of the user stack. And I'll explain what that means in just a minute, but it is implemented on x86-64 Linux and Mac and also on ARM64 Mac. Notably, it's not implemented on Windows. So stack memory, as you likely know, it's used for function local memory. It stores the return address and any local variables that that function needs to use, and also it's very fast and simple to allocate and deallocate memory using a single pointer, the stack pointer. So if you look at the virtual memory address space on Linux, or pretty much on all modern platforms, the stack pointer, it starts from these high memory addresses here, and as the stack grows, it actually grows downwards towards these low memory addresses. So that means that if we want to allocate memory on the stack, we actually need to subtract from the stack pointer. And if we want to deallocate memory from the stack, we actually do the opposite and we add to the stack pointer. So it's kind of counterintuitive, but that's the way it works. And so the thing is, even though we're told that we have a maximum of 4 megabytes of stack memory, or I guess anywhere between 1 and 8 megabytes, depending on the platform and whether it's a main thread or a secondary thread that you're spawning, the kernel doesn't actually reserve the entire 4 megabytes up front. Instead, it relies on the stack pointer to know exactly how much of the stack memory you're using at any one point in time. And so even though you have the ability to write to the stack below the stack pointer, there are actually situations in which the kernel will write directly to the user stack underneath the stack pointer and can overwrite any memory you have there. So one of the most common situations this happens in is during what is known as POSIX Signals. So this is an asynchronous event system that sends events from the kernel to your application, which is implemented by Linux and Mac. And one of the most common ones that you've probably seen before is if you're running your terminal application on Linux or Mac and you press Ctrl+C, it actually sends the SIGINT or interrupt signal. So if you go into your Mac or Linux terminal and you type kill-L, you can actually see a full list of signals that your system supports. So we can see number 2, SIGINT, the one I was just talking about. There's also, for example, number 11, SIG-SEGV. That's sent if your process has a segmentation fault. And even though by default, the behavior of most of these is to terminate the application, that actually doesn't have to be the case. So any of these, except for, I believe, SIG-KILL and SIG-STOP, you can actually write a handler for. So you can catch them and you can write a handler and you can do whatever you want with them. So SIGINT, for example, instead of making it terminate your application, you can make it do like a graceful shutdown. Or you can make it do nothing at all, ignore the signal, and just resume whatever your application was doing before the signal was sent. The way this works looks something like this. So you have your running Linux process, and when the signal gets delivered, the CPU jumps to the signal handler. But now, assuming that your signal handler doesn't actually terminate your application, once the signal handler completes, it needs to resume your application wherever it was when the interruption happened and the signal was delivered, and not only at that location, but also with the exact same state. So all of the CPU registers and so on need to be restored. So in order for it to be able to do that, it needs to store what's known as a signal frame. And it's important to note that this signal handler runs within the same user context as the rest of your application. Okay, it's not run by the kernel, which means that the signal frame needs to be available to the signal handler so that it needs to be stored on the user stack. And that's the reason why the kernel will sometimes write to the user stack below the stack pointer, which is why you need to be careful and not get your memory overridden. But on systems that implement the red zone, the kernel actually makes a promise. It says, hey, whenever I need to write to the user stack for a signal frame or any other purpose, I'm actually going to give you a 128-byte safety buffer. So the signal frame, it's not going to go into the red zone, it's going to go somewhere into the stack underneath the red zone. So what that means is if I write a leaf function, meaning a function that doesn't call any other functions, I can actually be lazy and I can skip my stack bookkeeping. I don't have to subtract to the stack pointer to allocate memory and then add to it to deallocate memory, I can just use up to 128 bytes of stack memory and not even bother. And you might be thinking, okay, and like, what's the point of this? Doesn't this just encourage sloppiness? But actually, it allows you to make optimizations, because if you imagine some sort of function that's called very frequently, and yet it has a relatively small number of instructions, the stack bookkeeping could actually represent a significant percentage of overall instructions. So I needed to come up with a function that actually makes sense to use with this kind of optimization. And I needed something very specific. It needs to be a leaf function. It needs to be something that can be optimized to use registers instead of the stack. It needs to use at most 128 bytes of stack memory so that it can fit within the red zone. And it needs to have a low number of instructions so that any potential stack bookkeeping would represent a significant proportion of them. And also, ideally, I wanted something that uses general purpose registers, because I haven't yet studied the SIMD, the single instruction multiple data registers. So I will admit that I used Gemini to help me come up with this, so I'm not a total hater. But basically what we have here, it's a proof of work function, and the client needs to brute force the nonce until we get a result, a hash that ends in 4 zeros. Or, this is adjustable depending on how difficult we want the work to actually be, right? And so, it allocates 64 bytes on the stack, and then it does some operations to the session ID and the nonce, and finally it returns the hash. And now I wanted to compare the assembly output of this function on Windows and on Linux. So this is a really great website, by the way, Godbolt. It allows you to compile with hundreds of different compilers and compiler versions and see the output in assembly. So for Linux, I'm using GCC, and I'm using it with an optimization level of 2, which is basically the default recommended for production applications. And so I don't want to go through this assembly line by line. I just wanted to stress one main thing, which is that we can see that we're not actually subtracting or adding to the stack pointer RSP, but we are accessing memory underneath it. As we can see here, RSP minus 72. Here we see RSP minus 8. And over here we have RSP minus 72 plus RDX times 8. So this is being used as indexing into the array. So we can see exactly the red zone in action. But now if we switch to MingW GCC, which is basically the Windows port of GCC, now we're going to see that the very first line is actually doing stack bookkeeping. So the first line is subtracting 72 bytes from RSP, and then the last line, or rather the second last line, it's adding those 72 bytes back. And so here we're actually not accessing any data underneath RSP. There's also a slightly different syntax. So instead of this being plus 64, the 64 is outside the brackets, and Windows uses slightly different register orders in function calls because of a different calling convention, but none of that is very significant. The main difference is really the fact that this one actually has to do the stack bookkeeping. So, we have here 37 lines, so minus 3 labels, that's 34 instructions. And so 2 of them are just subtracting and adding to the stack. That's about 6% of total instructions. And, obviously not all instructions are created equal. Not every instruction takes up the same amount of CPU power, CPU cycles. But nonetheless, as we're going to be running this millions of times on the client to brute force it, these 2 instructions, millions of times, that's actually definitely going to add up whether or not we have to bother with the stack bookkeeping. On the other hand, on the server, which only runs it once, it's not even going to notice the difference. So Windows decided not to implement the red zone. Instead, they wanted to prioritize having strict stack boundaries to make it fully observable during debugging. But on the other hand, Windows does actually have this concept known as shadow space. So basically, function callers are required to pre-allocate a 32-byte area of the stack for use by the callee. But shadow space is not intended as a general purpose local variable area like the red zone is. It's generally reserved for spilling the 4 register arguments into the stack, and I haven't really looked too much into it myself yet, so I won't say any more about that. But basically, those are the reasons why Windows doesn't implement the red zone. So now that we've seen how the red zone can optimize leaf functions, I also wanted to demonstrate its protective boundary in action. So I cooked up some code over here, which in assembly, what it's going to do, it's going to place some memory underneath the stack pointer, both within the red zone and also beyond it. And then we're going to print out the memory, and we're going to view it both before and after actually sending an interrupt signal to ourselves. So I'm going to go through this line by line. It should be fairly easy to understand, even if you've done very little assembly. So this is just declaring we're going to be using Intel syntax because GAS uses AT&T by default, and AT&T syntax sucks and everyone hates it. And now we're declaring main to be our global entry point, and also two external functions we're going to be linking against printf, and signal, which allows us to declare a signal handler. And so these are the constants which define the memory offsets from the stack pointer that we're going to be using, both for the red zone, so we're going to be placing it just at the very boundary of the red zone, and also for the other memory, it's going to be 1024 bytes underneath the stack pointer. And now this is our print macro. It's a macro because I'm going to be calling it twice. So basically it calls printf, and also it sets up the registers to have all of the correct arguments, because these are the format strings that are going to be passed in. I have two format strings. They're exactly the same, except one just says before and one says after. And they print out basically where we're looking at inside the memory. This is going to be passing in these constants over here. And then it prints out also the actual memory it's going to read in those locations. So this is just setting all the correct register arguments. And then one more thing, because this actually isn't a leaf function, so this part is important, I actually have to protect my, my stack from the printf function itself. So what I'm going to do is right before I call printf, I'm actually going to be moving the stack pointer to go beyond all of the data I've placed on the stack. So beyond the doomed offset, I'm going to call printf, and then I'm going to go back and deallocate that stack memory. So printf isn't going to be able to, mess up our experiment. It's not going to be able to touch this memory. But before we actually call the signal, we're once again, deallocating this, and the stack pointer will be back above all of the data we've placed. So this is our handler for the SIGINT, and basically it does nothing, so it's just going to return to where we were interrupted. And okay, so this is the main function. So initially, because again, this is not a leaf function, and there's actually a rule in x86-64 that we need to make sure that the stack is always at a 16-byte boundary, that it's always aligned to 16 bytes. So because when you call a function, in this case when you call main, it pushes the return address onto main, and a return address is 8 bytes, we actually need to allocate another 8 bytes onto the stack, even though we're not going to be using these 8 bytes in this case. So now we are registering the signal handler, calling the signal function, which we have imported and linked against from the standard library. And basically we're setting the RDI register, which is used for the first argument, to 2. So this is the SIGINT signal. And the second register, RSI, we are setting to the pointer to the empty handler that we just saw above, which does nothing, just returns. And then we call signal, so this registers the handler, and now it's registered. So after this point, if we get a signal interrupt, what's going to happen is that it calls the handler, and then it returns and resumes the code. Okay, so now we are actually writing our test values to the stack using hexadecimal. So cafe babe inside the red zone, and dead beef in the stack area beyond the red zone. And now we're going to print it once, passing in the format before string. And now we're doing a couple of syscalls in order to actually send the SIGINT signal to ourselves. So the syscall 39, called sysgetPID, gets our program's process ID. And then the syskill, which is syscall number 62, allows you to send a signal to a specific process. So in this case, argument 1 is the process ID. So that's the one we got from this syscall, which that syscall placed the result in EAX. So now we're moving from EAX into EDI, which needs to be the first argument to the next syscall. And then in the second argument, we're placing the actual signal we're sending. So in this case, SIGINT. And finally, we're doing the syscall. So at this point, the interrupt actually happens. It's going to move to the handler we created, and that's going to do nothing. It's going to return. So then it will resume back over here after the syscall. And now we have the second print. So now we're using the format after string, and now we're just doing some cleanup. So before we return, we need to actually set the stack back to, deallocate the 8 bytes, because the return will pop off the return address, and then so it's allocated again for the function that it returns to. And then before we return, we're just sending EAX, which is where we place the return value. We're setting it to 0. So if you XOR a value with itself, it sets it to 0. This is actually in assembly a little bit more efficient than directly setting it to 0. Okay, and that's it. So now if we actually go ahead and compile this, and then I'll just immediately run it. Okay, so we can see before the signal, we had Cafe Babe and we had Dead Beef. And after the signal, we can see that outside the red zone, it's actually become 0. And now it's not completely consistent. Like if I run it again, now we actually have some data in there. So, it depends on, in each iteration, where exactly the signal frame is being placed and what data is within it. But, sometimes it's 0 and sometimes it's some non-zero value. I tried actually playing around with the doomed offset. Initially, I placed it at 132, which is exactly beyond the red zone. And it didn't override it. And I guess the signal frame just wasn't hitting that point. And then, I tried different values like 256, and it was always 0, which I just found not as interesting. So that's why I went with 1024 for the main demonstration, because yeah, it was, sometimes showing some seemingly random data was more interesting than just zeros. But actually, I also noticed that if I go all the way down to 4096, at that point, it doesn't actually affect the memory. So I guess the signal frame is somewhere between 4096 and the red zone. It's not that far out. But basically, the moral of the story is that anything within 128 bytes with the stack pointer in the red zone, you can count on the fact that if you have a leaf function, it's not going to be overridden. But anything beyond that, basically, anything goes. So I also wanted to show that if for some reason, you don't like having to simulate the Control-C with a syscall, we can actually just do Control-C directly if we create a loop, an infinite loop. So I'm going to create a new section for data, and I'm going to create a global variable called exit loop, and it's just going to be a byte value defaulting to 0. And now, instead of these syscalls, we're going to get rid of that, and we're going to have a label here, and we're going to say compare and now basically if this and we're comparing with 1, and if this is equal to 1, then that means we're going to exit the loop and we're going to jump here to after loop. Otherwise, we're going to jump back to loop. And then in our handler, basically, before we return, we're actually going to move a value of 1 into this. So now, if we run it again, now we're in the infinite loop, and if I press Control-C, and here we go, same thing, except instead of actually sending the signal by code, we're actually doing it with our keyboard pressing Control-C. And I hate it when it's 0. There we go. So same thing, and you can do it in both ways.